which was accepted to ICML 2021. The outline of the talk is the following. So first I will give some brief introduction to distributed optimization and motivation for our work. So then I will describe implementation of Newton's method in distributed optimization. And then I will introduce our contributions with numerical experiments. Okay, so first, distributed optimization looks like this. So we have the server, this is the main machine, and also and clients, devices, or workers, call them as you want. So, and we want to optimize some, so we want to find some optimal parameters of some machine learning model using this architecture. We assume that the data is divided between these n machines, and each machine has its own local loss function fi. So let's look at how, for example, Newton's method can be implemented in this architecture. So each node computes local gradient and local Hessian. Then these things are broadcasted to the server. The server aggregates them and performs Newton's step in order to compute new parameters of our model. And then these new parameters are broadcasted back to the machines, to the clients. And this process is repeated. So the main problem of this architecture is this communication, just because the cost of communication is much more expensive than the cost of local computations. So that's why in distributed optimization, we do not optimize the number of steps to convergence, but the number of bits, for example, that were broadcasted from clients to the server. So this is the key difference between classic optimization and distributed optimization. Okay, so how we can handle this communication bottleneck? The first approach is to use local methods. So the pseudocode, for example, of local GD can be written as on the slide. So we perform t-1 iterations of local gradient descent. So each node perform such updates. And then each t iterations, we perform full gradient steps. So here the server is participating too. So the main idea how we can handle this communication bottleneck is to use, so we decrease the number of communication rounds. So this is the first approach. The next approach is compression. Here the idea is that we use some approximation of true local gradient, which requires less bits to be broadcasted from the client to the server. So this is another approach. And in our paper, we based on the second, on compression. Okay, so let me now give some brief motivation for our work. If we look at first order methods, for example, at compressed variants of first order methods, they are really good investigated in recent years, and they can probably benefit from compressed communication. So it means that compressed variants of some gradient type method outperforms non-compressed variant in terms of communication complexity. But the problem of first order method that the rates depend on the condition number. And also sometimes we have a problem how to tune the step sizes for these algorithms. Okay, so here you can see some examples also. So if we look at local methods, they are not so well investigated, and there are some papers which indicate that such methods are bad for heterogeneous data. And then the data distributions between two devices are far from each other, from each other. But these methods still have this problem, two problems, that rate depends on the condition number and the choice of step size. So one way how we can handle this problem in classic optimization, that we use the second order information about the objective. So, but in distributed optimization, all existing second-order methods suffer from at least one of the following problems. So as far as we know, the communication cost is too expensive. For example, we need to broadcast Hessians or some part of the Hessians, which is really expensive, or the rates still depend on the condition number. And this problem is a little bit controversial, just because in classic optimization, we know that Newton's rate doesn't depend on the condition number. So that's why the performance of second-order methods in distributed optimization can be even worse than first-order method. So our goal is to develop a communication-efficient Newton-type method. Those local convergence rate will be independent of the condition number. So this is our main goal of our work. Okay, so let's go next to the problem. So here on the slide, you can see some notation which we use. We consider L2 regularized problem, and each loss function is generalized linear model, and it has new Lipschitz second derivative. So this is a classic assumptions on for second order methods. So for brevity, I will use the following notation also. So the loss function, which so the local function which represent the loss on if node, I will define as fi, and the whole function that we want to minimize is capital F. And now let's look at Newton method again. So as I said, each node should compute local gradient and local Hessian. Then the node should broadcast them to the server. The server aggregates them and performs Newton step. So as I said, this method has local quadratic convergence rate independent of the condition number, but the communication cost again is really expensive because it is OD square. We need to broadcast D by D matrices, and this is a communication bottleneck of Newton's method. We want to decrease this dependency on D. So one of the theoretical idea how we can handle this is our first contribution. It is Newton star. The only difference with standard Newton method is that we use the Hessian at the optimum. So it is a really simple idea, but and we for a moment assume that we know the Hessian at the optimum. So now we need to compute the Hessian just once at the beginning. So we compute them, broadcast them to the server. The server aggregates and keep this information for the rest of the optimization process. And each node in each iteration also only need to compute local gradients. So this is some way how we can handle this communication bottleneck of Newton's method. And we have proved, of course, local quadratic convergence rate for this method. So it means that we use only one Hessian, but we do not lose any property of Newton's method. So we still have quadratic convergence rate. Here we assume that the Hessian at the optimum is low bounded by mu star times identity, and the sum of mu star plus regularization parameter lambda should be positive. Okay, so let's now briefly summarize the properties of this algorithm. So as I said, this theoretical idea solves both questions, both problems. We have local quadratic convergence rate independent of the condition number, and now communication cost is just OD because we need to broadcast only local gradients. But unfortunately, of course, we cannot implement it in practice because we do not know the Hessian at the optimum. So that's why it is logical that we need to approximate the Hessian at the optimum and do it better after each iteration. So, but first, let's look at the structure of the Hessian. Our methods are based on this structure. So here we additionally assume that each loss function is convex. As a consequence, its second derivatives are non-negative. And here regularization parameter is positive. So that's why this first term can be represented as a conic combination of rank 1 matrices. So this is the structure of the Hessian. Okay, well, let's go next. So our next contribution is Newton law. So our desire here is to approximate the Hessian at the optimum iteratively and do it effectively in terms of communication complexity. So here matrix HK can be written as you can see on the slide. So the only difference is that we use some coefficients, Hij, instead of the second derivatives. So, and we will learn these coefficients. Our first desire is to learn these coefficients in order to, we want the converge to the second derivatives of loss functions at the optimum. But the update, which belongs to if node, so this is a coefficient which belongs to if node, this update should be sparse. So for example, we update only 1, 2, or for example, 3 integers of this vector, or some only 3 elements, for example. Yeah, and of course we want the local rate to be independent of the condition number. So this is our wish list. So now let me introduce our learning mechanism for these coefficients. So it is based on the learning mechanism from which was introduced in the paper about Diana method. This is a first order method. So we perform Diana-like update and then project onto non-negative orthant. So we project onto non-negative orthant just because, as we remember, second derivatives are non-negative. So that's why our coefficients also should be non-negative. So, and also this is important just because we need this term should be positive semi-definite matrix. And here we use compression operator. So we use unbiased compression operator. The definition is given on the slide. So the simplest examples of such compression operators is random specification. So, or just random error. So let's look at how random 2 compressor works. So let's assume that the input of this compressor is this vector, and the output, as you can see, has only 2 non-zero elements, and the rest of them are 0. And now we also multiply by some fraction in order to make the output to be unbiased. So now this, as you can see, this vector requires less bits to be broadcasted from the client to the server if we compare with the input. So, and this compressor has variance parameter omega is equal to m over r minus 1. So it means that we can control this variance. So for example, if r, our random specification parameter, is equal to m, so this variance is just 0, and our compression operator is just identity. So I would like to know that this parameter can be chosen as we want. Okay, so, and also in this update rule, we have step size eta, which only depends on the compression variance omega and doesn't depend on the condition number. Okay, and we have proof local linear convergence rate for this algorithm. So here phi is Lyapunov function, which can be written in such way. So the first term of this Lyapunov function is responsible for convergence of parameters of the model. And the second one is responsible for convergence of our introduced coefficients Hij. So equivalently, it means that it is responsible for convergence of our approximation Hk to the Hessian at the optimum. So, and also I would like to note that the rate doesn't depend on the condition number. It only depends on the compressor, just because it only depends on the compression variance. So it means that our desire is satisfied. So, and also I would like to mention that since our Lyapunov function converges, then it means that our desire also about convergence of Hessians is also satisfied. Okay, so this is our contributions. Here I have described two methods from the list of from the paper. This is they are Newton star and Newton law 1. I have not described the second result for Newton law 1. It's just some simple consequence of convergence of Lyapunov function. So we also have some modification of Newton star, which we call Max Newton. We also assume that the Hessian, the optimum is known, but we create the matrix, the matrix a little bit different for Newton step. And this method leads to the second. This Max Newton method leads to the second Newton law algorithm, or just NL2, which handles the case then the regularization parameter lambda can be 0. So now we can use it as we want. So we can add regularization or we can hide it. And also we have globalization technique, global convergent method, which is based on cubic regularization. So you can see that it has global convergence rates and also local linear and superlinear rates. So this is the list of our methods. Okay, so and now let's compare our methods with some classic baselines. So the first one is, of course, is Newton method. So we compare them in terms of communication complexity. So here, the x-axis is communicated bits. We compare them on artificial data set, and we use logistic regression model. So, and as you can see from these plots, the convergence, so the difference between these our methods and Newton method is significant, so 8 times faster. So this difference can be larger if we use larger data sets. So, and also we compare our methods with existing state-of-the-art algorithms in distributed optimization. So this is an accelerated Diana, which uses Nesterov momentum and some also, and the Diana trick that was mentioned before. So, and also Dingo, this is the second order method, the best second order method in distributed optimization. And also we compare it with BFGS in order to compare some kind of quasi-Newton method and with classic quasi-Newton method. Yeah, so and here you also can see that the difference between our methods. So our methods are much more communication efficient than these ones by many orders in magnitude. So that's why we hope this new approach is really promising and should be investigated. So actually, we have some next paper which handles some problems of this one. So for example, we do not assume some special structure of the functions. So this is the end of my talk. If you have any questions, I will please to answer.
Thank you, Rustem. Any questions? Hi, Anatoly Yuditsky. Can I ask a question?
Yes,
Yeah, sure.
All right. So could we come back to when you described the rates for Newton methods, and there were this slide exactly, yeah. So there is the convergence region and how it corresponds. What are these lambda? Just excuse me. Just could you recall what are these parameters and how does it correspond to the normal convergence region of the Newton?
So actually here so we can look at regularization parameter lambda as a strong convexity constant, yeah, and also nu times r of power 3 can be connected as a Lipschitz constant of the Hessian. So that's why the convergence area of this method is the same as for Newton's method. So we have mu over h. The mu is strong convexity parameter and h is Lipschitz constant for Hessians. So maybe the difference with some constants, but it is not so important, I think.
Okay, so what you said is essentially the same.
So actually, yeah.
So you pay no price for randomization. And could we come back to the slide with simulations? Just
simulations.
Yeah, the next one, I think. Okay, so actually the logistic regression. This is a very nice function. It's almost okay. It's not self-concordant, but almost. But what I was wondering is you present the result. You solve this problem up to accuracy 10 to the power minus 15.
Yeah.
And basically in this, because this function comes from learning applications, there is absolutely no need to solve the problem to such accuracy. So when you compare, when you look at the accuracy like 10 to the power, you did not say what are the dimensions, what are the parameters m, n, and so on, but I doubt that the number of observations are millions or what.
So this is in some sense toy examples, because d, the parameter d here is about 200, 100 or 300 elements. So the dimension of x is the following, and the number of nodes and the number of and the size of local data set is, as I remember, is about, so the number of nodes is about 100 also, and the number of data points in local data set is about 1,000 points.
Okay, so actually, I think that solving to the accuracy 10 to the power minus 4 or even 3 would be okay for statistical applications. So, and when you look at this, that basically BFGS or even first order methods, they're pretty they compete quite well, no, at this range.
Yeah, if we look, yeah, of course, if we look, for example, at the accuracy of this of logistic regression problem, so maybe at the beginning they will be that maybe these methods, Adayana Ding and BFGS, can compete with our, but our approach is to find the exact solution. Of course, if we want to just to find some good approximation of the solution, so in this case, first order methods, for example, will be better.
And I was actually wondering about the problem, like, you know, there are problems like minimization of quadratic function over simplex, right? Or L1 ball. And I was wondering what would be the result of applying Newton method, your version of the Newton method to this problem, because there is a celebrated, there is a celebrated problem with complexity of this one. Because the upper bound, which is dimension independent upper bound, which is by Uri-Nestor, it's the accelerated algorithm is 1 over t square, and the lower bound, the best as far as I know, it's like 1 over t to the power of 5 or 6, something like this.
Yeah, but actually it is only convex problem, so we consider strongly convex cases.
Yeah. It's just minimizing a quadratic function over a convex quadratic function over a L1 wall.
Yeah,
Okay.
I understand, but I mean that our case is strongly convex case.
Okay.
I mean, so we hope that this local superlinear rates, which is independent of the condition number. So if we, of course, this is really just the beginning of this approach, this new approach, and we should create, for example, better globalization strategies. But we hope that these local rates are really some good point. So this is our idea of the paper.
By the way, logistic function is not strongly convex.
Yeah, but if we add regularization parameter, it is strongly convex.
Okay. Thank you.
Thank you. Any questions also?
Yeah, I have a question on the algorithm Newton round. Do you have to communicate the AIG, or do you assume that they are sent at the beginning to the server, or do you communicate them each time?
So yeah, this is a good question. Thank you. So I would like to note, that we also need to broadcast the hashing at the zero, so at the beginning of optimization process. So just once. This is a requirement for convergence. And yeah, so if we want to update this the hashing approximation, we need to know these data points. So in our numerical experiments, we assume that the server doesn't know them. That's why we need to broadcast them in each iteration. So we calculate this cost too, the cost of this communication.
Okay, so they are accounted for in the communicated bits that you shown, like for your experiments.
Yeah.
Okay, thank you.
So, and this is really some disadvantage of this algorithm, but as I said, this is just the beginning, and we handle this issue in our next paper. So because then we share local data, it is a little bit bad if we look at the implementation in practice.
Thank you.
Okay, thank you. Thank you, Rustem, for your great talk. We have the second presenter, Egor Shulgin, with his talk, Accelerated Decentralized Optimization Method for Time-Varying Networks. Egor, please, let's start.
Hello, can you hear me well and see my slides?
Yes, yes.
Okay, great. So, hi everyone. My name is Egor Shulgin, and I'm a master's student at King Abdullah University of Science and Technology and the Moscow Institute of Physics and Technology. I'm happy to present our recent paper called ADAM, Accelerated Decentralized Optimization Method for Time-Varying Networks. And I would like to thank the organizers for inviting me and for organizing this great workshop. So this is a joint work with Alexander Rogozin and Alexander Gasnikov from Moscow Institute of Physics and Technology in Higher School of Economics, Dmitry Kovalov from KAUST, and Peter Riftarik, who is my current research advisor. In this work, we consider an undirected network G with V being a set of nodes from 1 to n, and E being a set of edges. Our goal is to find a solution of a finite sum minimization problem over RD, where each data describing function fi is available to the corresponding node I only. So this constraint may come from some physical, may come from physics when we have just some set of agents that can communicate only with its neighbors, and they don't want to share their data with anybody else. So privacy constraint sometimes lead to such decentralized settings. In our paper, we focus on the case when each Fi is L smooth and mu strongly convex. As for decentralized setting, communication is done only across the edges of the network. In this example, node 7 can communicate across edges with nodes 3, 6, and 8. And on every round, it can communicate only across its neighbors. And this applies to every node in the network. We use the gossip matrix W to represent the decentralized communication. This is an n-by-n matrix which satisfies 3 properties. It is symmetric, positive, semi-definite. Wij is non-zero if and only if I is equal to j, or I is a neighbor of j, and the kernel of W is a consensus space. Decentralized communication can be represented as a multiplication of a vector by a gossip matrix. This is a classical theme in decentralized optimization, and indeed the ith component of Wx is a linear combination of xj of all j's that are neighbors of I. So this can be checked very easily by hands, and this gossip matrix usually encodes the topology of the network, and one of the typical choices for this matrix W is just the graph Laplacian of our network. In this work, we studied the situation when the links in the communication graph are allowed to change over time. Such a setting may be relevant for sensor networks, where changes in the link structure occur when the sensors are in motion and due to some other disturbances in the wireless signal connecting pairs of nodes. Mathematically, time-varying network is represented by a sequence of graphs where every GK is just a connected, undirected graph with a certain gossip matrix WK. So we work in the same setting, but this graph can change on every iteration. If there are any questions regarding this decentralized setting, I would like to pause here for a couple of seconds. If there are no questions regarding this, I guess I can move on. Yeah, so next, I would like to do a few reformulations of the original problem. So you can have a look at it one more time. So at first, we just have a finite sum, which is classical to almost any machine learning task. And firstly, we would like to consider an equivalent lifted problem with the consensus constraints. We denote the objective function of the lifted problem by capital F. And in this case, the main difference is that at the beginning, we had just single vector x, which may correspond to just weights of some model, of some machine learning model. And this vector is the same for every node. But when we consider the lifted problem, these vectors can be different for every node. And there is a set of vectors x1 to xn. And here x corresponds to this kind of stacked vector. And to make this problem indeed equivalent, we impose this consensus constraint. The lifted problem has an equivalent dual formulation where f asterisk is the functional conjugate of function f. In this case, the constraints is also slightly different. So in this case, we have a set of dual variables, z1 to zn, and the sum of zi must be equal to 0. This is also a quite classical thing for decentralized optimization. And there were also some previous works that considered the dual approach. And it is in some sense simpler than the primal approach. And for this dual formulation, we assume that we have an access to the dual gradient of the local functions, which is not always the case, but in some applications, we actually have access to these dual gradients. For example, for some rich regression tasks, or for softmax minimization. In optimal transport problems, dual approach can be also beneficial. So it makes sense. And when we don't have access to the true dual gradient, we may also approximate it. And I will speak about it further. And now let's move on to the algorithm for this dual problem. And a natural way to tackle it is to use a version of projected Nesterov's accelerated gradient method, or PNGD. Here, P is an orthogonal projection matrix onto the dual problem constrained subspace. This algorithm converges with the optimal rate, square root of kappa times log 1 over epsilon, where kappa is the condition number of the function f. However, PNGD in each iteration calculates the matrix vector multiplication p times the dual gradient of f, which in fact requires full averaging over all nodes in the communication network. And unfortunately, this cannot be done in a decentralized fashion. So this kind of method is not suitable for our case. And the key idea of our work, which kind of helps to solve this issue, is that decentralized communication can be seen as the application of a specific contractive compression operator. So the contractive operator is defined here. And this is a standard thing for distributed optimization. And Rustem also said a few words about it. And if you just stare for a couple of seconds at this formula, and you notice there's this decentralized communication. Indeed, if we denote by this sigma times W, the operator, this contractive compressor, then this inequality is basically the same as the definition of a contractive compressor. And please note that the highlighted operator is linear, but it may be biased. And in distributed settings, it can be a serious issue because methods can diverge if we use biased compressors. That's why we need to utilize the error feedback mechanism. And what I described on the previous slide, this idea suggests using compressed gradient descent as soon as we have some compressor. And as I said, it may not actually converge. And this is a problem which is usually fixed by this error feedback mechanism, which is presented on the slide. So we have a little bit of modified version of the original error feedback. And instead of compressing the gradient update, we typically want to send from some worker to the server. this mechanism works with a compensated vector. So here, this vector mk usually corresponds to the memory. Error feedback performs a compressed gradient step with this adjusted vector. And then it updates the memory vector, which is basically the difference between what we wanted to send and what was actually transmitted. So this is basically the compression error that we have on the current iteration. And the combination of this error feedback mechanism with the Nesterov acceleration leads to ADAM, which is described here. I don't expect you to parse it at this point. ADAM corresponds to basically accelerated decentralized optimization method, and it is suited for time-varying networks. And the main thing that you should see here is that that I would like to highlight here is that we use the following terms to characterize the complexity of the method. So here, the blue terms correspond to communication complexity. So on every iteration, we communicate these vectors, and we communicate them because there is the W operator, which, as I said before, corresponds to decentralized communication round. So the complexity of the algorithm is measured by two terms. The first one is the communication complexity, how many decentralized communication rounds we need to actually find the solution. And the second thing is the gradient complexity, which in this case corresponds to the dual gradient, but usually gradient complexity is interesting when we speak about primal gradients. So I don't want to spend a lot of time on it. And next, I would like to present you a review of some decentralized optimization algorithms that are capable of working in the time-varying network regime with guarantees. And here, complexity terms highlighted in red represent the best node dependencies. So ADAM is the only method with the right dependencies in all terms. And in this way, it achieves the new state-of-the-art rate. And this is, in fact, optimal. And you can see this preprint by Dmitry Kovalyov et al. In this preprint, you can find the lower bounds for such kind of problems, and the optimal algorithm, which uses only the primal gradient. So it is dual free. Next, I would like to move to some experimental results. We compared with the best previous methods on the L2 regularized logistic regression problem for different optimization and network parameters, he and kappa. So kappa characterizes the condition number of the problem, and he characterizes the condition number of this sequence of graphs, of communication graphs that we used. In this case, we just simulated the time-varying network as a sequence of geometric random graphs with Laplacians chosen as this matrices WK. And to summarize the results, ADAM converges linearly, and it outperforms all other methods for basically every set of parameters, as it was predicted by the theory. And you can also find much more experiments with synthetic real data and real networks in the full paper. So here I just presented only like 4 plots, but in the full paper there are much more results. So thank you for your attention. I would be happy to answer any questions.
Thank you. Do you have any questions?
Yes, so I have one question. So could you please describe the key differences of centralized and decentralized settings?
Mm-hmm.
And why we are interested in decentralized setting?
Mm-hmm.
So why can't we use just?
Okay, so one of the issues with the distributed centralized setting may be the case when the number of devices is very huge. When like the n using our previous notation is very huge. In that case, it may be a problem for the server to aggregate all the updates from the workers when the number of workers is very huge. In this case, it may be easier for these workers to communicate in a decentralized fashion. So, in fact, distributed case is just distributed centralized case is just a special case of this decentralized optimization when this graph is like fully connected, when every node is connected to all other nodes in the network. In this case, the settings will be basically equivalent. And another thing which kind of motivates this decentralized setting, as I said, this may come from some physical constraints when we just don't have a central coordinator, and we can work only with maybe we have some drones that can communicate only to drones that they can see. Maybe they can transmit to some limited distance, and not every drones are inside this ball, which allows for communication. So they can communicate only to their neighbors. So I hope that clarifies.
Yeah, thank you.
Yeah, thank you for the question.
So any questions else? Okay, then the question from me. Could you please show the plot with comparison with baselines?
You mean the theoretical complexities?
No, I mean the last, I think, slide or
experimental results.
Yeah.
Mm-hmm. Okay.
Great plots, but I have a question about the first top, the top left first plot and the right bottom. Why there is some break in the Adam performance in the small number of communication rounds? I mean, there is some piecewise linear function that can be seen there.
Mm-hmm. Mm-hmm. Yeah, so to be honest, I don't have like a very good like answer to this. So sometimes this just happens with optimization methods that like converge linearly. That maybe at the beginning, a few rounds is enough for the method to already have a good solution. So in this case, just a couple of communication rounds is enough to have this like accuracy of 10 to the power of -7. Yeah, but one of the issues is that in this particular case, the number of communication rounds to converge, for example, to like 10 to the power of -15 is really huge, because the condition number is larger than in this case. So this is kind of a problem of a scale that was chosen. So I mean, if we just choose a smaller accuracy, this won't look so strange. Yeah.
Okay, thank you. So any questions else? Okay, then I think we should glad you for your talk. For your talk, thank you. And we have a break for half of an hour, and then we will continue. Thank you.
Yeah, thank you for your attention.
Okay, let's continue our workshop. The next presenter is Roman Isachenko. He will talk about dimensionality reduction for signal decoding. Roman?
Hello, yes. 1 second. So I'm ready.
Okay, let's start.
Hello, everyone. My name is Roman Isachenko, and I'm a PhD student at MIPT. The topic of my today talk is dimensionality reduction for signal decoding. In this study, we are considering the problem of selecting the optimal decoding model. The decoding process essentially is a process of restoring the dependencies between two heterogeneous data sets. The challenge that we are considering is the case where target variable is a vector. The spaces of the input signals and target signals have excessive dimensionality, and dimensionality reduction methods that do not take into account dependencies in the target space are not adequate. We propose to reduce the dimensionality of the input and target spaces by projecting signals into the latent spaces with significantly smaller dimensionality. Linear and nonlinear methods for building concordant models are proposed. Our goal is to build a decoding model F, which takes the input signal X and predicts the target signal Y. The slide shows an example of the input and target time series for the task of restoring the hand trajectory based on the signals of the electrocorticogram. The input and target signals have a different nature and have a high dimensionality. A point in the X space is a segment of the input signal from the space of dimension n. A point in the target space Y is the segment of the target signal from the space of dimensionality R. The complexity of this problem lies in the fact that in each moment of time t, the forecasting decoding model have to predict a vector consisting of successive moments of the target signal. To construct an adequate model F, we propose a procedure for dependencies concordance. In order to do this, the input and target signals are projected into the latent space, which has a smaller dimensionality compared to the dimensionality of the original data description. The operators P and Q restore the input and target variables from the latent space projections. At the same time, it's proposed to concord the projections in such a way that the covariance between the projections is maximum. Let's consider the case of a linear signal decoding model. The input and target variables form the X and Y matrices. The model parameters theta are a matrix. We will use the simple quadratic L2 loss function between the target variable and the forecast for this decoding model. If there is a strong multi-correlation between the columns of the matrix in the frequency domain of the input signals, the decoding model turns out to be unstable. In this moment, we propose a method of projection data descriptions into a latent space. The original matrices X and Y are projected into latent spaces. The matrices T and U are the images of the original matrices. The commutative diagram shows how the method works. It finds the maps W and C from the spaces X and Y to the latent spaces T and U, as well as the inverse mapping P and Q. We propose to concord the projections in the latent space. In this case, we find the link operator B in the form of a linear model for concording latent spaces. The final decoding model is linear, but has a low-dimensional latent representation. We solved the problem in the assumption of high redundancy in the data description. To find the optimal low-dimensional manifold, we introduce a latent space notion. The general scheme of concording dependencies for the decoding problem is shown in the following commutative diagram. If there exists invertible encoding function phi e and psi e and decoding functions phi d and psi d, we will say that for the input and target spaces x and y, there are latent spaces t and u. In this case, latent spaces are concordant if there is a link function h which maps objects from one latent space to another. To find the encoding and decoding functions and the link function, the task of projection concordance is posed as maximizing the concordance function J. We proposed the iterative procedure for finding projections with maximum covariance. A theorem of the optimality for model parameters of the concordant decoding model has been proved in the case of concordance function as covariance function. Here on the slide, one can see an example of how the projection method works in a latent two-dimensional space. The blue and green dots represent the input variables and the target variables x and y. The input variables are generated from a normal distribution with covariance matrix sigma. The target variables depend linearly on the second principal component of x and do not depend on the first principal component of the matrix x. The red contour shows the level lines of the covariance matrices. The black arrows correspond to the vectors of the matrices W and C. When we reduce the dimensionality of the input space without taking into account the existing dependencies in the target space, using, for example, the principal component method, we get an inadequate solution. Using a concordant latent space, the model is able to find the optimal latent subspace of dimensionality 1 given by the operators W and C. This takes into account the interdependence between the images of the X and Y matrices. To build the model selection procedure, let's consider the case of an additive superposition of decoding models. The overall decoding model is the sum of two separate models. And the goal is to obtain an algorithm that answers the question about the need to include a specific model in the general superposition. We have proved the statement about optimal parameters of each of the model in the superposition. And also we have proved this theorem on the optimality of the model superposition over each particular decoding model. A procedure for selecting models in the superposition is proposed based on the analysis of subspace projections constructed on linear span of the original data descriptions. In addition to linear decoding models, we consider nonlinear methods. In this case, the encoding and decoding functions are deep neural networks. Each neural network is a superposition of matrix multiplications and element-wise activation functions. The concordance process consists in maximizing the concordance function according to the parameters of each neural network. Using neural networks, the decoding model is able to take into account significantly nonlinear dependencies both in the input space and in the target space. And if correlation is used as a concordance function, we could get expression for the gradient of the concordance function. And this expression for the gradient allows us to build an effective algorithm for solving the problem using gradient optimization methods. To get a simple model and moreover analyze the importance of specific features, let's consider the problem of choosing the optimal feature subset. The goal of the feature selection problem is to find a binary vector A whose components are indicators of the selected features. We introduced the loss function S for this feature selection problem and the vector Z that contains the importance values of the initial features. So the decision to include a feature in the final decoding model is made by cutting off the importances by some threshold. The loss function of the decoding model for this case takes into account only the selected features which are given by the binary vector A. To analyze the feature dependencies, we consider filter method for feature selection using quadratic programming approach. This method finds a feature subset using a quadratic function S, minimizing the pairwise similarities of the original features and maximizing the relevances of the original features to the target vector. We have proved that when using the spectrum shift of the similarity matrix Q as a semi-definite relaxation, the quadratic feature selection problem has a unique global minimum. The complexity of the problem that we consider is to take into account dependencies in the target space. To generalize the method to the case of a vector target variable, we use the method of aggregating relevances by target vectors as our basic strategy. Thus, the relevance vector B is obtained by summation of correlations across all target vectors. The drawback of this method is the lack of accounting for dependencies in the space of the target matrix Y. We propose the generalizations of the original method to account for these dependencies. Symmetric importance strategy penalizes correlated target vectors by introducing a matrix of pairwise similarities QY for target vectors. Thus, in addition to taking into account the interactions of the initial features, the feature selection loss function takes into account the interactions of the target vectors. Symmetric importance strategy leads to small values of importances for target vectors that are weakly correlated with features and large values for the target vectors that are strongly correlated with the features. To account for the target vectors that are weakly correlated with the initial features, it's proposed to add a penalty term for the target vectors that are weakly correlated with the initial features. And in this case, the contributions of features and target vectors becomes asymmetric. If we have target vectors that are weakly correlated with the initial features, we propose a min-max feature selection problem. It has been proved that in the case of positive definite matrices of pairwise similarities Qx and Qy, the min-max problem is equivalent to the quadratic programming problem, and min-max and max-min problems have the same value of the loss function. To obtain a convex problem, we also could use semi-definite relaxation as previous. To sum up, in addition to the basic strategy of relevance aggregation, we have proposed 3 methods for feature selection problem to account for dependencies in the target space. It has been shown that all proposed strategies are generalization of the original method for the case of a scalar target variable. We also propose an algorithm for optimizing nonlinear models using the considered quadratic programming approach. For this purpose, we introduced the concept of active model parameter. An active parameter is a parameter theta j that is able to decrease the loss function using the second order gradient optimization method. We have proved the the theorem on the form of the loss function for the selection of the active model parameters when we use the Newton method for optimization for this nonlinear model. The slide shows a two-dimensional model example of choosing a single active parameter when optimizing the model. For the practical analysis of the proposed methods, we introduced the following quality criteria. The normalized error indicates the quality of the forecast. The multi-correlation coefficient is responsible for the stability of the final decoding model, and Bayesian information criteria is a measure of the complexity of the model. We consider the problem of building a brain-computer interface as an applied problem. The goal is to build a forecasting decoding model that restores the hand trajectory from the signals of the electrocorticogram. Both the space of the input signals and the space of the target signals have an excessive dimensionality, which is redundant. The initial signals of the electrocorticogram form the matrix X. The target signals of the hand trajectory form an after regressive matrix Y. The components of the target variable are strongly correlated along the time axis. On this slide, we show the described quality criteria for all the methods that we consider. The proposed methods have a smaller error, are more stable, and choose a simpler model in relation to the basic strategy relevance aggregation. We also compare the method of projection to the latent space with the methods of feature selection. The picture on the left shows that for this problem, the optimal dimensionality of the latent space is significantly less than the dimensionality of the original data descriptions. And the proposed methods achieve a smaller error compared to well-known methods such as lasso and elastic net. The best result is achieved by a combination of two approaches. It's PLS plus CubeFS. To conclude, we have proposed the methods for signal decoding that take into account dependencies in both the input and target spaces, and methods for selecting concordant models in the case of excessive dimensionality of spaces. We have proved the theorems on the optimality of the proposed methods. We also have proposed the methods for feature selection that give stable and adequate solutions in the correlated spaces of high dimensionality. Also, we have got nonlinear methods for concording latent spaces, and the proposed models allow us to build an effective forecasting system for heterogeneous data sets, for example, for the brain-computer interface problem. Thank you for your attention. I will be glad to answer your questions.
Thank you for your talk. Any questions, please? Okay, then the question from me. Have you tried any other concordance functions other to correlation?
It's the problem here is if we need a closed form solution for linear models. And it's very difficult to use nonlinear concordance functions in this case. For the nonlinear methods, such as deep neural networks, we tried to use small neural networks, such as 2 or 3 layers MLP, and this gives better results. But it's difficult to get any theoretical results in this case. So yes, we could try it, but we can't prove it.
Okay, thank you. And just another question about the form of nonlinear models, for example, for neural networks. Did you try some generative models? And if yes, does your approach works with generative models? For example, with wire or something like that?
No, the short answer is no.
Mm-hmm.
It's a good idea to try. Yes, maybe in future work. No, now we didn't consider any generative models such as Wire, GANs, or something like that.
Oh, okay.
I have a question, if I may. So you have target space, three-dimensional, since it's a space of hand motion, of hand movement, right? It moves in 3D, and you have, say, 4 or 64 channels. Why do you call these spaces of high dimensionality, and why do you call these spaces multi-correlated?
You mean the question about target space, why it's high dimensional if it has only 3 components?
Yes.
Because our goal not just to predict one moment of time, we would like to predict the trajectory for not one moment of time, but some time segment. And in this case, our matrix Y, which is shown in this slide, becomes large. We have lots of target vectors, and these successive moments of times are correlated. And if we look at the correlation matrix, we will see that moments of times are really correlated. X, Y, and Z components could be not correlated at all. Yes, it's true. But if we considering some moments of time, we have correlations, and the simple approach to reduce the dimensionality that do not take into account these dependencies are inadequate, and it could be shown in the 2 examples. So yes, if we do not have high dimensional target space, we could use the simple usual methods. But if we have correlations and if we have structure in target space, the model should take into account these dependencies.
Mm-hmm. Thank you.
Thank you. Any questions also? Well, I think no. Then thank you, Roman, for your talk.
Thank you.
Our next presenter is Antonina Kurdyukova, detection of phase of human motions with signals of wearable devices. Antonina, please.
One moment, I will share my screen. I hope now you can see the slide.
No.
No?
Yes, now, yes.
Okay. Hello, everyone. My name is Antonina Kurdyukova, and I'm a third-year student at MIPT. I'm very pleased to perform today on the workshop, and I would like to deliver a talk about the phase detection of human motions with signals of wearable devices. It is a joint work with Denis Tikhonov, Georgy Kormakov, and Vadim Strizhov. If you have any question, I will be grateful if you could leave them until the end. The current generation of portable mobile devices, such as cellular phones or music players, is becoming increasingly complex. Most of these devices incorporate various types of sensors, including accelerometers, light sensors, cameras, microphones, and GPS sensors. That can be applied for analysis of everyday human behavior. its important part is human physical activity that reflects various aspects of health and thus is exceedingly attractive for many applications in the field of healthcare monitoring. So in this work, the goal is to construct a model that determines the phase of the time series trajectory. The problem is that human motion is quasi-periodic. An example of quasi-periodic time series is a time series of human gait, such as walking, running, or leaping. We suppose that each studied time series of human gait comprises a fundamental period connected with the cycle of gait. During the cycle of normal human gait, each lower limb goes through a stance phase and a swing phase, and then returns to the stance phase. To solve the problem, we reduce the dimensionality of the trajectory space. The criterion of dimensionality is the phase trajectory does not have self-intersections. Then we form phase trajectory approximation, and phase is reconstructed from the obtained trajectory. Let S sub E, where E is from 1 to n, be given the original time series. Define the Hankel matrix of the time series that you can see on the slide. N is the window of the length, or is the window length, and the length is not less the sum supposed period. Let S sub Q be the column of the Hankel matrix, and note that all vectors S sub Q form the phase trajectory. The principal component method reduces the trajectory space dimensionality. The obtained vectors x sub q form the trajectory space of reduced dimension p. Okay, let me repeat the main idea. The original time series S is given, and S sub q is a point of the time series. We construct the Hankel matrix H, and its columns form the phase trajectory. We suppose that the dimensionality of original trajectory space is excessive. This leads to instability of forecasting models for the series. And then we project the trajectory to some subspace, and analysis of trajectory subspaces simplifies the structure of the phase trajectory. So you can see on the left picture the original time series of human gait, and on the right picture you can see its phase trajectory, and inside it is approximation of this trajectory. This is some close works. The first paper addresses the problem of segmenting neural periodic time series into period-like segments. To split the time series into periods, the author selects a pair of principal components of the Hankel matrix, and then cuts the trajectory of the selected principal components by its symmetry axis, thus obtaining half periods that are merged into segments. The second paper proposed a method for human physical activity recognition using time series collected from a single triaxial accelerometer of a smartphone. Primarily, the method solves a problem of online time series segmentation, assuming that each meaningful segment corresponds to one fundamental period of motion. And the last paper analyzes the periodic signals in the time series to recognize human activity by using a mobile accelerometer. Each point in the timeline corresponds to a segment of historical time series. These segments form a phase trajectory in phase space of human activity. The principal components of segments of this phase trajectory are treated as feature description at the point in the timeline. So all these works use the idea of working with time series by phase space, but there is no any algorithms that allow us to obtain a phase of time series, but if we have the values of phase, we can also obtain the period of quasi-periodic time series. Now I'd like to say the idea of dimension reduction or of trajectory space. Let's write the trajectory matrix H in more detail. N is its window length. Then we compute the singular value decomposition of its matrix. Then select principal components in a quantity of p vectors, where each vector is equal to h multiplied v sub q, where vectors v sub q obtained from the matrix V in the decomposition. And for these components, we reconstruct the trajectory matrix, where each component is equal to lambda sub g, the eigenvalues squared multiplied by v sub g, and multiplied by each component y sub g transposed. Then we perform the rotation and get a reduced dimension trajectory space. Now let's describe the approximation of the phase trajectory. We approximate the phase trajectory by the model G, which sets the point of the average trajectory E and the value of the variance D in accordance with the phase phi, which is between 0 and double p. In the work as a model G, we used the Nethereye-Watson regression. The corresponding formula you can see on the screen, and the value of the variance can be calculated as similar. Let me comment this formula. The length of the window is h is fixed. You can see phi prime. It is a value of phase assigned to the point x sub e from the trajectory space with assumption about the period of time series. Also, when introduce a metric, it is equal half of 1 minus cosinus phi prime minus phi. We introduce a metric in order that the distance between angles, for example, 0 and double p was 0. Now I'd like to tell some words about dimensionality reduction in the experiment. We call the subspace where phase trajectory does not have any self-intersections the minimal dimensional trajectory space. So what does mean self-intersections? So points which have significantly different phases or which are far removed in time, but their trust areas intersect. So I mean that there exist indexes E and G, and the corresponding value of phases phi sub E and phi sub G different more than, for example, p to 4. And trust areas we express by the values of variance of points x sub E and x sub G from the trajectory space. Let's talk about a phase detection model. We will call the points x, E, and x sub G neighboring if their two norm are less than epsilon, where epsilon is a hyperparameter. So to extract the phase, the model is based on two assumptions. The first assumption is a point with a large index corresponds to a large phase. I mean that if index G is larger than index E, then the phase phi sub G must be larger than phase phi sub E. And the second assumption, the phases of neighboring points must be close. So now we can set the optimization problem to extract the value of phase. We need to minimize the loss function, which have two components. The first component is corresponds to the first assumption, and the second component corresponds to the second assumption. Let me show you the result of algorithm work. For time series used in the experiment, the third dimension where self-intersection are absent is equal to 4. It means that the minimal dimension for this time series is 4. On the picture, you can see trajectory space, and points are colored according to the value phase obtained. Inside the points, you can see the yellow line. It is a model approximation for our trajectory, phase trajectory. Experimental results confirm that the algorithm works well. The model assumptions are completed, so the points that are close in space have similar colors, and a point with a large index corresponds to a large phase, so points are ordered by color. Note that the points along the same radial direction have the same color. In conclusion, I would like to say that in related work, we firstly developed an algorithm for phase extraction of a quasi-periodic time series. Secondly, phase trajectory approximation problem quasi-periodic time series was solved. And the last, we proposed a criterion for detecting self-intersections of the average trajectory. That's all I would like to say. Thank you a lot for your attention. And now I'll be happy to answer your questions.
Thank you. Please, questions.
Antonina, in the previous slide, you said that the trajectory does not intersect itself. So, but we see at least 1, 2, 3 intersections.
Okay. I said that for this time series, the minimal dimension where there is no intersections is equal to 4. But in the picture, the dimension is 3. It is, and if we would get higher dimension, we wouldn't see any intersections. But now to show you the results, we get the 3D picture.
So we just reduced the dimensionality from 4 to 3 so that we could see this trajectory.
Yes.
Okay. Mm-hmm. So what is the precision you obtained of the approximation of the phase trajectory?
Precision. So the question is how we obtain precision, or?
No. Yes.
So we can put the difference between points of phase trajectory from all points to the mean trajectories that approximate our trajectory.
Mm-hmm. Okay, thank you.
More questions? Oleg asked me to be a, to host a conference to continue.
Thank you very much.
Sorry, yes, I understand. I should say about it. Okay, if there is no more question, I guess we can move on.
Okay, thank you.
Alexander vanished. Wait, sorry, Alexander. Then I will announce the next speaker is Alina Samokhina with her talk.
Sorry, I see how it works. Okay.
No, it's okay. Yes, Alina, please present yourself.
Hello, everyone. No?
Yes, share your screen and go on. Alina is a master student.
Okay, so you can hear me, you can see the presentation, everything okay, right?
Yes, please. Continuous time representation for signal decoding. Excellent.
Yes, hello. So my name is Alina Samokhina, and I'm a MIPT student, and I'm going to talk today about continuous time representation for signal decoding. The goal of this research was to construct a time continuous model of a signal, because there is a wide problem of constructing the phase space, but it's done only with discrete time, and we want to see how the phase spaces would work with the continuous representation of time. So at first, we should construct a time continuous model of the signal. Besides the scientific interest, we also have a real-world motivation. It is application to signals from wearable devices, such as accelerometers or electroencephalogram things. What for? To resample the signals recorded at low sampling rates and to process irregular in-time data when the contact with the device is intermittent. We want to build a neural interface to model multidimensional time series. We suppose that if we can use recurrent neural networks, whose hidden state can be represented as a solution of an ordinary differential equation, then we can work with the time series as with the continuous in time. We can obtain the time continuous representation of the signal, and we'll do that while we are building a neural interface. To model time series, we will use recurrent neural networks and neural ordinary differential equations. We are talking about neural brain-computer interfaces, neural interfaces, and the paradigm we're working in, it's P300, let's call it P3. P3 paradigm, it's a paradigm for neural interface where our brain activity, we can see on right graph, we have a response in our brain activity when some outside stimuli is presented. For example, if you're looking at some object and this object starts to move or changes its brightness, then here on the left picture in the occipital lobe, we will have a change of a brain activity. We will call this target EEG segment. If it has this peak, and if it doesn't have, it will be non-target EEG segment. To sum up, we have some continuous process, brain activity. We have recorded signal, electroencephalogram, realization of this process. We want to do the simple classification task of 4 EEG segments, whether it has P3 or whether it doesn't. But we also want to say that if we have such a realization, we can construct a function f so that this function would approximate our signal and it would be a continuous function. We based our work on 3 main papers. The first paper is the origin of neural ordinary differential equations, where authors just introduce a concept of working with neural networks as with the solution of ordinary differential equation. And 2 other works, the guys tried to apply approaches from the first paper to irregular time series. But mostly authors focus on some modeled data set, not real world data. So we will focus on real world data. And we have a data set of the 3 potentials. It is EEG segments, number of electrodes, and to number of timestamps in the EEG segment. It's our feature space, and our target variable is 0 or 1. It's simple, just a binary classification task, whether there is a P3 or there is not. In other aspects, it's just a simple binary classification task. But well, as I already said, the main interest is continuous time signal representation, which we can obtain while we're constructing this neural interface. We suppose that we can use the hidden state of neural ordinary differential equations as a continuous signal representation. Why can we do this? We assume that this hidden state can approximate the signal so that our solution would retain the shape of the process, is continuous, so that our function would deliver values at any point in time. And a small technical moment, we should use such an architecture so that we can extract a hidden state from the model and use it as an independent function. What models can we look at? First one is controlled differential equations, and how it works. We have our process realization, then we have some approximation as a natural cubic spline, and then we say that our hidden state would be a solution of the following controlled differential equation. We're getting our initial hidden state and then solve controlled equation, and on our hidden state we're doing the classification. Later I will show you that hidden state Z actually is a continuous representation of the original signal. Another model was also considered, Legendre memory unit, LSTM, because many papers said that simple recurrent neural networks like the previous one would have a fading gradient problem, and we should try to see it LSTMs. We actually have very short EEG segments, so we wouldn't have this gradient problem, but still it's interesting to look at. Here we have a state vector M, which is like memory vector, and it's also sliding window of our signal by Legendre polynomials, so that we can do this thing with our signal representation. We can decompose it into D Legendre polynomials with the coefficient. It's not equality, it's multiplication, sorry. So Legendre polynomials with the coefficient taken from the state vector. Computational experiment was held to see how these models behave in the classification task. We wanted to compare the performance of our algorithms with neural ODE and the ones we used in practice earlier. Also, we want to see if we can really obtain a continuous time signal representation. We use the data set of P3 potentials, Demons P3. This data set contains EEG recordings for healthy people playing in virtual reality. How this is going? You have some visual stimuli, 3, 5, and this stimuli, they change its brightness, and while brightness changes, you have a P3 peak in your occipital lobe. Okay, as we can see in the table and the slide, here presented 4 different models, neural CDE, LMO-LSTM with neural ODE, and EEG-net. It's a convolutional neural network designed specifically to classify the electroencephalograms. And Pi-Riemann model, simple logistic regression with some feature preprocessing in terms of Riemannian geometry. So the first 2 models, especially the first one, is actually better in accuracy and F1 score than other models. So we can say that even for the ordinary regular data, these models sorry for my English. These models can be used not only for some irregular data, but for quite ordinary one, and still will be improvement on alternative models. But when we have irregular data, or we want to prognose target variable in times other than the moments we get the signal. For example, we are getting signal every 2 seconds, and we want to predict our target variable every second. So these neural ODE models to the rescue. Hidden state of Legendre memory unit LSTM wasn't quite what we were looking for. That's why I'm talking only about the hidden state of neural CDE. It meets all the criteria for continuous time signal representation we set. And we see that it's not an exact description of the process, but still it retains its shape. We can see the peak here and there. And also that can be obtained at any moment in time. Here we have 100 points of Z for each point of the incoming signal. So to sum up, in this work was proposed a continuous time signal representation. Models were compared with alternative approaches. And for further research, it was suggested to look at some other neural ODEs, like the Bayesian ones, to obtain other signal representations, compare them between each other, and then consider this representation or their parameters as the approximation and of new feature space for tasks involving electroencephalograms and time series. Thank you for your attention. I bet you have a lot of questions. I will be glad to answer them.
Antonina, thank you. Thank you. Please, questions?
About P300, am I right if I say present you a stimulus, like I show you a coffee mug first time, and then I will show the same mug the second time. So the second peak P300 will be bigger or not?
I suppose no, because
You're learning this coffee stimulus, Mac stimulus.
It's not that you should learn the stimulus, or that the more you show it, the more is P300. Usually, especially for brain-computer interfaces, it is used in a way that you have a static object. So like you have a standing coffee mug, and then, for example, you turn on the lights that that spots this coffee mug, and then you have a P300, something like this. But its amplitude doesn't depend on how many times the brightness will change. So it's more or less the same amplitude from time to time.
Okay, but again, for the it looks like a peekaboo game, cuckoo. Nobody
like
yes, for the first time, nobody recognized Mama, and after several times, the peak increases more and more, and we could use it in our modeling, or not.
No, it's not about recognition. It's just about reaction to the change in the environment.
Mm-hmm. Okay, thank you.
Thank you. I have a question, Antonina. As far as I understand from the title of your talk, you are motivated by concrete applications. Maybe you say a few words about where your research applied in industry.
Okay, yes, I had some of the real world applications in mind. I can say that it's already used somewhere in industry, but I think that for some devices with intermittent contact, it would be useful. I know that some other models are used somewhere, but I'm not sure I can tell you where.
Okay, thank you, thank you. So, any questions?
Yes, could I ask a question?
Yeah.
So just so maybe I could better understand, if we come back to the example of EEG signals, just so what is the input? So it's just the control, like control linear system time. So what is the input, and yeah, maybe at the end. And when you present the results, so what are the measure of accuracy, and well, is it possible to see simulated, true signals and the prediction and things like this? So what was the sampling?
Okay, I'll answer the question as I understood it. So I'm sorry if I won't get it the first time. The input signal is electroencephalogram. It is a matrix of size, number of electrodes, like E times n, number of electrodes times number of time points that we have. Here, the only one graph plot I have, we have 40 points in time, and there are 8 channels of electroencephalogram which look like this. I think that plotting predictions isn't a very good idea because it's a classification task, and I can't imagine how I will do this. Here we see the incoming signal, like some channel of our electroencephalogram and its hidden state. About accuracy, about accuracy, it's actually pretty simple accuracy. How much class labels we got right.
Okay, so the accuracy is measured by class labels.
Yes.
Just now, actually, I was asking about the model of the signal. I mean, so what is the input of the model? So you have a time continuous model which is measured on the discrete grid, right? But what is in this situation? What is the input? What is the dynamics of the model?
Okay, I'll try this. For the model, we have first we are doing in the model. We're having an no, not in the model. 1 second, I'll formulate this just right. We have S, our approximation of our process, and as an input to a model, if I'm not mistaken, we are taking the coefficient of this natural cubic spline approximation. Then inside the model, we are doing what? We are solving the control differential equation. At first, we have some initial hidden states. We obtain initial hidden state, and then we solve the ODE with some numerical methods, and then with this hidden states, we are doing the last the classification layer. I'm still not answering your question, right?
Okay. Thank you.
Actually,
timing.
Thank you.
Yeah, thank you. And I propose to thanks one more time speaker and move to the next talk. Thank you.
Thank you.
Thank you. And next talk Alina Samokhina, continuous time representation for signal decoding.
No,
Alina?
it was me
Yes.
already. I wasn't Antonina, I was Alina. Thanks.
Oh, sorry. One moment. Oh, blin. Yes, I understand. Okay, so the last talk, I guess, Vladislav Goncharenko, Contemporary ML Ops Instruments. Vladislav, are you here? Vladislav, I don't see Vladislav in Zoom participants. Okay. Вадим Викторович, получается, это был последний доклад?
I guess yes. It was the since we have no Vladislav and Rudislav, then it will be the last talk. Okay, Alina, thank you very much, and friends. Then we will meet here exactly tomorrow at 9 o'clock Central European time to continue with the talks about the deep neural networks and how to select models of machine learning. Thank you very much.